Hello, this is Dr. Baxley. This is a video lecture for part of Chapter 3 about how to determine chemical formulas from empirical data. This is something that's very important to chemists, coming up with those formulas of different compounds. How is it possible to get the formulas for compounds without knowing their names? Let's say you make a compound and you don't really know what it is, you just know what elements are present. How would one go about figuring out the formula for that particular compound? Well, you're going to learn how to do that in this video. I suggest that you have your printable lecture notes available for Chapter 3 while watching this video, because the video will follow along with the notes and examples. Sometimes it's important for chemists to calculate the mass percent, or the percent composition in a compound. This is the fraction by mass of one element in the compound. It's easy to calculate. It's the mass of the element divided by the mass of the whole sample times 100%. Here's an example for calculating the mass percent of sulfur in lithium sulfide. First, we'll start with the formula and molar mass of lithium sulfide. Once we have the molar mass for lithium sulfide, we can find the mass percent of sulfur in 1 mole of the compound. Simply dividing the mass of the sulfur by the total mass of the compound, multiplying by 100%, will tell us the mass percent of sulfur in the compound. Subtracting that from 100 can tell us the mass percent of lithium in the compound as well, which would tell us that the percent by mass of lithium is 30.22%. Let's move on to figure out how to determine the formula for a chemical compound. Keep in mind that chemists, when they're determining formulas for new compounds, need to know 2 pieces of information. We need to know the qualitative part, what elements are present, and we need to know the quantitative part, what mole-to-mole ratio those elements exist in. We have to use moles to determine the formulas for mass or mass percent data. It's easy to measure mass of compounds. It's much harder to measure moles. Once we've measured mass, we then have to use the molar masses to calculate moles to figure out that mole-to-mole ratio in a chemical formula. Here's an example. The question is, what is the empirical formula for a compound that is 88.81% oxygen and 11.19% hydrogen? We can use the percent by mass to figure out the relative masses of each substance in this particular compound. We'll start by assuming a 100-gram theoretical sample size. Assuming the 100-gram sample size, we can see that there'd be 88.81 grams of oxygen and 11.19 grams of hydrogen. Once we know the masses of each of the elements, we can use those mass values to calculate moles. Dividing those masses by the molar mass will allow us to calculate the moles of each of those substances. Now, we can't write a formula for this compound of oxygen and hydrogen like this with these numbers of moles, because we know that the numbers of atoms in a molecule need to be whole numbers. In order to get these values into whole numbers, we can divide by the smallest value of moles. In this case, the smallest number of moles is the moles of oxygen. So dividing through by 5.551 gives us 1 mole of oxygen and 2 moles of H. And now everyone can see that this molecule is good old H2O. We can see a general pattern in this type of problem solving. And that general problem solving pattern is that the mass percent of the elements can be used, assuming a 100-gram sample, to find the grams of each element in terms of mass. We can then use the atomic weights, or molar masses is a better term, to calculate moles of each element. We can then calculate the mole-to-mole ratio and determine the empirical formula. Of course, 2 tips were that the atomic weight is better termed the molar mass, and that after calculating the mole-to-mole ratio of all the elements, you sometimes need to divide by the smallest value of moles to get everything to be whole numbers. If you're given mass percent information, start at the top left of this diagram. You assume the 100-gram sample and calculate the mass of each element in grams. Sometimes, if you're just given directly the mass information, you can skip that first step and calculate grams of each element. If you were given moles of each element, you could start even later in the process and start in the lower right-hand corner of the diagram. Let's look at one more example. But before that, the main point is that we have to use mole-to-mole ratios. The formulas for compounds are not mass ratios, they are mole ratios. Here's the next example, where a compound consists of two different masses, one of silver, one of bromine. The question is, what's the empirical formula for the compound? Following that diagram on the previous page, you might be able to come up with a few steps for how to go about solving the problem. Go ahead and read through the problem, think about the diagram and the steps you might need to take, and try to solve it on your own. Pause the video while you're solving, and then restart the video and see if you've gotten the correct answer. The general pattern for solving this type of problem is to start with mass, convert to moles using the molar mass, and then calculate the smallest whole number ratio. This particular example is fairly straightforward, and that's because using the molar mass and the number of grams of each substance, we find that the number of moles of silver and bromine are identical. The formula, therefore, must be AgBr, just like you'd predict from the periodic table. Here's the next question. A compound consists of 45.5% by mass tin plus some chlorine. What's the formula for the new compound? The first thing to think about is to try to figure out how much, as a percent by mass, the sample must be for chlorine. Once you've determined that the sample must be 54.5% chlorine, now is the time to get to work and figure out what the mass of each substance would be in this compound, how many moles of each there would be in the compound, and then what the empirical formula would be. Go ahead and pause the video and see if you can answer the question on your own. Restart the video and watch for the solution. Using the molar mass of each substance will allow us to calculate the relative number of moles of both tin and chlorine. Now we need to take the step of dividing through by the smallest number to calculate the relative number of moles of each one in whole number terms. Once we do that, we can see there's 1 mole of tin and 4 moles of Cl, so the formula of the compound must be SnCl4. Here's our next problem. It's about a sample of vitamin C, which contains carbon, hydrogen, and oxygen, and we're given the mass percentages of just carbon and hydrogen. The question is going to be, what's the empirical formula of vitamin C? We're then going to take this a little step further and calculate the molecular formula also. You should be fairly comfortable with the steps by now. Pause the video and give it a shot. See if you can come up with the empirical formula for vitamin C. I've calculated first the mass percentage of oxygen, and then I've used the molar mass of carbon, hydrogen, and oxygen to calculate the number of moles of each substance. Let's see what happens when we divide through by the smallest number for the number of moles. Dividing through by the smallest number of moles still leaves us with a fractional number. At this point, the proper step is to start multiplying each of the number of moles for each element by small whole numbers until you're able to clear the fraction. Start with 2, then go to 3, 4, 5, and see what happens from there. You should be able to get within plus or minus 0.1 of a whole number before you can stop rounding. Multiplying by 3 ends up clearing the fraction. The value for the empirical formula ends up being C3H4O3. However, this formula may or may not be the molecular formula for this particular substance. Now it's possible for many compounds to measure the molar mass of the compound with experimental techniques. It turns out that the molar mass of vitamin C works out to be about 180 grams per mole. However, the fragment of C3H4O3 doesn't weigh 180 grams per mole. Calculating the molar mass of this particular substance gives us 88.1 grams per mole, very much different than 180 grams per mole. We can use these two numbers, though, to figure out what the molecular formula must be. We can divide the approximate molar mass of 180 grams per mole by the molar mass of our empirical formula at 88.1 grams per mole and come up with a ratio of those two numbers. This ratio works out to be about 2. We can therefore multiply the empirical formula values by 2 to calculate the real molecular formula for vitamin C. We can see then that the molecular formula, how the molecule really exists, should be 6 carbons, 8 hydrogens, and 6 oxygens for every 1 molecule, or that number of atoms in moles per mole of molecules. And this would be our molecular formula.